The canonical commutation relations. In the last class, we looked at translations, and from the properties of translation, we found that the commutator of xi with xj is 0, the commutator of pi with pj is also 0, and the commutator of xi with pj is I h bar delta ij. These relations form the cornerstone of quantum mechanics, right? You could develop quantum mechanics by starting with these commutation relations. In his book, Dirac calls them the fundamental quantum conditions. More often, they are known as the canonical commutation relations or the fundamental commutation relations. All right, so these are very important. These are fundamental to quantum mechanics. Now, if you want to look at it historically, Heisenberg was actually studying the atomic transition lines at that time. So he was looking at certain experimental results. Now, he saw that he actually realized that this could be understood or described if he associated arrays of numbers with these frequencies. All right, so there are certain frequencies, there are certain transition lines. He found that he could associate arrays of numbers with these frequencies. All right, arrays of numbers. And he found that in order to describe these results, these arrays of numbers actually have to obey certain multiplication rules. And so he developed a new theory which involved these arrays of numbers and which had certain particular multiplication rules, right? In such a way that these experimental results could be understood. But actually, Heisenberg himself did not know that he was working with matrices. Right? Matrices was known to mathematicians at that time, but Heisenberg had no idea. So it was actually Born and Jordan who actually pointed out that Heisenberg is working with matrices. Right? So Heisenberg's multiplication rules they found was nothing but the multiplication rules of matrices. All right, and they showed that the theory could be developed on the basis of these kinds of commutation rules, but among matrices. All right, here this we said in general these are commutation rules among operators or observables. All right, operators, Hermitian operators. All right, so they saw that they could develop a theory if they started with certain commutation relations among matrices. Right now, this branch was known as matrix mechanics. Now, Dirac also was looking at these things, and he realized that the various quantum mechanical relations, okay, for example, the commutation relations, the fundamental commutation relations, can be obtained from the corresponding classical relations just by replacing the classical Poisson brackets by commutators. Okay, so he actually realized that there seems to be a deep similarity between the quantum mechanical commutators and the classical mechanical Poisson brackets. Right? In fact, he found that you can go from a classical theory to a quantum theory, right, by replacing the Poisson bracket or the classical bracket, if you like, right, the Poisson brackets by a commutator bracket divided by IH bar. Okay. Now, you may remember that classical Poisson brackets are defined for functions of q and p as if you have functions of q and p. This is how you define the Poisson bracket of two functions, right? Two functions of q and p. It involves this partial derivatives, all right? It's partial derivative of a with respect to qs multiplied by partial derivative of b with respect to ps minus the partial derivatives taken in the opposite order. Okay, partial derivative of a with respect to ps multiplied by partial derivative of b with respect to qs. Right? Now you have to sum this thing over all the coordinates and momenta. All right. These are called the Poisson brackets. For example, in classical mechanics, you have this Poisson bracket relation. Xi with Pj, the Poisson bracket of Xi with Pj is delta Ij. All right, you can easily check this by using the definition of Poisson bracket. You could also take this as one of the fundamental Poisson bracket relations. All right. Now, Dirac's idea says that if you have a classical mechanical relation like this is classical mechanical. Okay, we can go to the quantum theory by writing, right, the commutator between the corresponding operators divided by IH bar is equal to delta Ij. All right. So instead of Poisson bracket equal to delta Ij, we say the commutator divided by IH bar equal to delta Ij. right? So that's what this means. If you have a classical bracket, you replace it by the commutator bracket divided by IH bar, and that will give you the quantum mechanical relations, right? So in quantum mechanics, this turns into commutator of xi with pj is equal to IH bar delta ij, which indeed are the correct commutation relations that we have already seen. Now, Dirac's rule works because the classical Poisson brackets and quantum mechanical commutators satisfy similar algebraic properties, right? They have similar properties. For instance, all these relations can be proved either by assuming that these are Poisson brackets or by assuming that these are commutators, right? The following relations can be proved regardless of whether these brackets is understood as a classical Poisson bracket or as a quantum mechanical commutator. I think you might have already proved some of these relations using Poisson brackets. Okay. Now, I leave it as an exercise for you to try and prove these relations, assuming that these brackets are commutators. Right? The first one is trivial. AA minus AA is 0. The second one, commutator of AB is AB minus BA, whereas the commutator of BA is BA minus AB. Right? We see that these are minus of each other. So if I interchange the objects in a commutator bracket, I get a minus sign. It's antisymmetric. And similarly, it's easy to see that the commutator of A with a number, commutator of an observable or an operator with a number is always 0. All right. And then we have this relation A plus B comma C is equal to A comma C plus B comma C. You can distribute it. Okay. So I ask you to prove this. You just use the basic definition for commutator. Commutator of A comma B is equal to AB minus BA. All right. So you multiply these two things in both orders. All right. Subtract them and see if we can write it. If you can write it in this form. All right. We have this relation. Commutator of A with BC is A comma B multiplied by C plus B multiplied by commutator of A with C. Right. Let's actually try to prove this here. Right. This is an important, useful relation. So this is A with BC, the commutator of A with BC. Okay. Now, based on the definition of commutator, I can write this as ABC minus BCA. All right. But this doesn't immediately look like commutator of A comma B with C plus commutator of B, plus B multiplied by commutator of A and C. All right. It doesn't look immediately like that, but you can put it into this form by adding and subtracting a BAC plus BAC minus BAC. All right. Now, if you look at these two terms, ABC minus BAC, this is AB minus BA multiplied by C, or this is A comma B multiplied by C. Right? I'm just combining these two terms. Right? Now, if I look at these two terms, this is actually plus. We have got this B here. Right? B is common here. So this is AC minus CA, or the commutator of A with C. Okay. So this relation is proved. Now, there's also this important identity which you might have already seen from your Poisson bracket classes. Okay, this identity is called as the Jacobi identity. I'll just state it and I'll leave it for you to prove this thing. All right. So this is the commutator of A with the commutator of B and C plus the commutator of B with the commutator of C and A plus the commutator of C with the commutator of A and B. All right, if you add all these things, all right, you see that it's a cyclic permutation ABC, BCA, CAB. Right, if you add all of this, it's 0. This is known as Jacobi identity. This is true both in the case of Poisson brackets and in the case of commutators. In fact, all these relations hold true in case of Poisson brackets as well as commutators. Okay. Okay, but there are also important differences between Poisson brackets and commutators. Right. First, the dimensions of the classical Poisson bracket differs from that of the quantum mechanical commutator because of the differentiations with respect to Q and P appearing in the expression for Poisson bracket. Right. We know that in the expression for Poisson bracket there are derivatives with respect to Q and P. Whereas in case of commutators, we are just multiplying the operators in different orders and then subtracting. Right? So this, because of this, there's a difference in the dimension of the classical Poisson bracket and the dimension of the quantum mechanical commutator. And second, the Poisson bracket of real functions of Q and P is purely real. Right? So if you are talking about functions of Q and P, the Poisson bracket is purely real. Right? But if you look at the commutator of two Hermitian operators, it is anti-Hermitian. Right? So in the world of numbers, if we use the word real, right? In the world of operators, we have got Hermitian operators. Hermitian operators. All right. So in the world of operators, real means Hermitian in a way. Okay. All right. And we know that if you want to talk really about numbers, if you take the matrix elements or the expectation value of an anti-Hermitian operator, you'll see that these imaginary or complex numbers will start appearing. Okay. So in the case of Poisson bracket, the Poisson bracket of real functions of Q and P is purely real. The commutator of two Hermitian operators is anti-Hermitian. Right? Now, to take care of these differences, the factor IH bar is inserted. The factor IH bar is inserted in this relation. So we said that if you have a Poisson bracket relation, you can go to the corresponding quantum mechanical relation by replacing this with the commutator. So whatever this Poisson bracket is equal to, we'll say the commutator divided by IH bar is equal. Okay, so if the Poisson bracket is equal to something, we said this is equal to the commutator divided by IH bar. Okay. But we have avoided using Dirac's analogy in obtaining the canonical commutation relations. Right? We could have obtained the canonical commutation relations using this Dirac's analogy. Okay, we could have started with the Poisson brackets and say that xi with pj, Poisson bracket is delta ij. Right? Now, Dirac's rule or Dirac's idea says that instead of saying that xi with pj, Poisson bracket is delta ij, I'll now say that the commutator of xi and pj, actually the corresponding operators, divided by IH bar is equal to delta ij. And we have got the canonical commutation relations. All right, we can get all these canonical relations using Dirac's analogy. Okay, but our own approach in this course is different. All right, we actually derived the commutation relations, the canonical commutation relations, based on the properties of translations and the identification of the generator of translation with momentum operator. All right, except for a universal constant. Okay, so where did we get this commutation relations or fundamental commutation relations? We did not go from the classical theory to the quantum theory. What we did was we looked at translation, right, and we identified. Again, we used some classical intuition. So we said that whatever generates the translation has to be called the momentum, right? And we fixed the dimensions by inserting a universal constant with the dimension of action. That's how we did it. Okay. Now, we believe that this approach is more powerful because it can be generalized to situations where observables have no classical analogues, right? So even though Dirac's idea is useful, right, you cannot use it everywhere because there are observable with no classical analog, right? There are observables in quantum mechanics with no classical mechanical counterparts, right? For example, if you talk about the spin angular momentum components, right, they have nothing to do with P and Q of classical mechanics, right? So you cannot start with classical mechanics and get an observable called spin, or we cannot get the corresponding commutation relations, all right? But we'll see soon that spin angular momentum commutation relations can be derived using the properties of rotations, just like we derived canonical commutation relations using the properties of translations, all right? So the spin commutation relations can be obtained, derived using the properties of rotations. Okay. So now we have the fundamental commutation relations or the canonical commutation relations, which are given by the commutator of xi with xj is 0, the commutator of pi with pj is also 0, and the commutator of xi with pj is IH bar delta ij. Okay. So these fundamental commutation relations form the cornerstone of quantum mechanics. Right? Let's solve a couple of problems using these commutation relations. All right. The first problem is to evaluate the commutator x with p raised to n, right, in one dimensional case. In one dimensional case, all right. One dimensional case means we have got an x and a corresponding p, that's all right. So we could actually evaluate this by starting with the commutator of x with p, right. This is equal to IH bar. What about the commutator of x with p square? Right? Let's find this also, right. This can be written as the commutator of x with p multiplied by p, which in turn can be written as p multiplied by x comma p plus x comma p multiplied by p, right. Here I have just used this rule. The commutator of a comma bc is equal to a comma b. This is equal to commutator of a comma b multiplied by c plus commutator of b multiplied by commutator of a comma c. That's the rule that we are using here. This x commutator of x with p is IH bar. Here also you have an IH bar. So you can, now these are numbers, right? We have got p multiplied by IH bar. There would be an identity operator also, right? But this IH bar and this p commute. So it doesn't matter where I put this. This means that I simply have 2 IH bar p. This is commutator of x with p square, all right? Let's now find the commutator of x with p cube. Alright. Now this can be written as commutator of x with p multiplied by p square. Again, I can use the same rule. Okay. This is written as commutator of x comma p multiplied by p square plus p multiplied by commutator of x comma p square. Right. I've just used this rule. I've just applied this equation. Right, I first take x comma p multiplied by p square plus p multiplied by x comma p square. All right. Now what is this? X comma p is IH bar. So this is IH bar p square plus p multiplied by the commutator of x and p square. We have already found here it is 2 IH bar p. So this is p multiplied by 2 IH bar p. That's p square. There's a p here. Since these are numbers, I can bring them together. So that becomes p square and then 2 IH bar. So if I add these things, this is 3 IH bar p square. Okay. Or let me write this as IH bar multiplied by 3p square. Right. Now we can continue calculating this. Using this result, you can find the commutator of x with p raised to the power of 4. Right. Now you can find, similarly, you can use the same thing. You can write x, the commutator of x with p raised to 4. Right. You can write this as p multiplied by p cube. The p cube relation can be used from here. Right. And you'll see that this is equal to IH bar 4p cube. Right. So this works generally. Right. So in general, we can write commutator of x with p raised to n. Right. So if you continue this, we see that the commutator of x with p raised to n can be written as IH bar np raised to n minus 1. Right. We can write the commutator of x with p raised to n as IH bar p n IH bar np raised to n minus 1. Right. So here we see that this is simply the derivative of p raised to n with respect to p. Right. So taking the commutator of x and p raised to n, so the commutator with x, you get a derivative with respect to p basically. Right. We get a derivative with respect to p. Is that correct? Because the commutator of x with p raised to n is IH bar. There's an IH bar appearing. IH bar multiplied by the derivative of p raised to n with respect to p. That would give us the same result. All right. Okay. So we have this interesting result. The commutator of x with p raised to n is equal to IH bar n p raised to n minus 1, which also can be written as IH bar. This is nothing but the derivative of p raised to n with respect to p. Right. So the commutator of x with some p raised to n, this is a function of p, gives you IH bar, the derivative of this function with respect to p, not with respect to x, but with respect to p. All right. We could check if this is generally true. All right. So we are asking this question: if you have the commutator of x with some function of p, if you have the commutator of x with some function of p, can we write this as IH bar, the derivative of f with respect to p? Can we write it like this? Right? The answer is yes. We'll show it. Right? Now, to prove this, one way to prove this is to start or to expand this function in a series. All right? So we write f of p is equal to sum over n. We can write this as sum over n a n p raised to n. All right? So this is nothing but a series expansion of this function. Right? So we assume that this function is well behaved and it has a series expansion. All right? So we are not talking about any exotic functions. We are just talking about normal, well-behaved functions. All right? And it will have a series expansion like this. All right? This is basically what we call the Maclaurin series. You know how to expand. You are familiar with this Taylor series, Maclaurin series, etc. We know how to expand, all right? You know how to calculate these coefficients. Here we don't need the coefficients. Only thing that matters is that we can expand this function as sum over n a n p raised to n. Well, this is a series expansion of this function. All right. If you want to know these coefficients, you just use the Maclaurin series, and you will see that you can write this. You can find these coefficients as derivatives. Right, these coefficients are associated with the derivatives of f with respect to p, etc. Right, but we don't need that here. We just need this series expansion. All right. Now, if I substitute this here, the commutator of x with f of p is equal to the commutator of x with sum over n a n p raised to n, the series expansion for this function. Right. Now I take this sum over n a n outside, and I have got the commutator of x with p raised to n. Okay. Let me continue it here. Okay. Now this is sum over n a n. This we have already calculated. Commutator of x with p raised to n. Okay. Which is I h bar n p raised to n minus 1. Okay. Now this can be written as sum over n I h bar, or let me write it like this, a n I h bar. This can now be written as the derivative, right? The derivative with respect to p of p raised to n. Right? This n p raised to n minus 1 can be written like this. Right? Now these are derivatives with respect to p, so I can take it outside. Right? This acts only on this p raised to n, so I can write this as this is derivative with respect to p of this summation sum over n a n p raised to n, a n p raised to n. All right, and I also have this IH bar. I also have this IH bar here. All right. Now what is this? This was the function that we started with. So this is IH bar, partial derivative of f with respect to p. Okay. So indeed this result is true. Right. The commutator of x with any function of p, right, is actually equal to IH bar multiplied by the derivative of f with respect to p, the derivative of f with respect to p. All right, this is a relation that will prove to be useful, right? Okay. Now, in a similar manner, we can also find the commutator of p with f of x. Okay. Now you can already guess this thing. All right, this is equal to minus IH bar, right? Because there's p comes first and x comes second, so there will be this minus sign. So it's minus IH bar, the partial derivative of f with respect to x, right? Partial derivative of f with respect to x. All right. Now you might already relate this commutation relation to the fact that momentum are the generators of translation. Momentum are the generators of space translation. All right, so I leave for you to interpret what this actually means. All right, if you take commutator of x with f of p, I get IH bar and derivative of f with respect to p. All right, here if I take p with f of x, I'll get minus IH bar derivative of f with x. All right, with respect to x. All right, so I leave it as an exercise for you to check this. Okay. We can generalize these to 3 dimensions. If you want one component of the x vector, and if you want to take the commutator with some function of p vector, right? Some function of p vector, it can be shown using the same kind of arguments. It can be shown that this is equal to IH bar, the partial derivative of f, right? So here I have xi, so you have to find the derivative of f with respect to the corresponding pi, right? If this is x1, then the derivative will be with respect to p1, right? In other words, if this is x, the derivative will be with respect to px. If it's y here, the derivative will be with respect to py. If it's a z here, the derivative will be with respect to pz. All right. Okay. Similarly, here we can, in the other case, we can write this relation as pi with some function, let's say some other function g. Maybe I'll write f itself, f of x vector. All right. We see that this is the derivative of this function with respect to the ith component of position. Right? There's also this minus. So this is minus ih bar. The partial derivative of f, okay, partial derivative of f with respect to xi. Right? If this is the ith component of momentum here, then the derivative is with respect to the ith component of position, etc. All right. Okay, I think with that we'll conclude our discussion of commutators for the moment. Right? We might be using some of these relations later on.